You're welcome to my YouTube channel, Mersthub Mentors. In today's video, we will talk about advanced array manipulation. Here we're looking at Einstein summation, which is known as Einsum. NumPy's Einsum function is a powerful tool for performing complex mathematical operations on arrays. It is based on the Einstein summation convention, which is a way of representing mathematical operations in a concise and elegant form. I will show an example. Here we have a dot multiplication of two arrays, or what you can call matrices, or some can refer to some as tensors in some cases. Okay, such that the output dimension is I times j, or I comma j. So here you have an array A which is of dimension I comma k, multiplying an array of B of dimension k comma j. By using the Einstein summation, the dot multiplication of these two arrays will be summed over the dimension k, such that the output dimension becomes I comma j. Now, to use the Einsum function, you will have to write a string that represents the operation you want to perform. This string is called the subscript string. The subscript string is a comma-separated list of subscript labels, where each label refers to a dimension of one of the input arrays or tensors. Specifically, the Einsum can be used to multiply unlimited number of arrays. And it's very powerful in the sense that it allows you easily manipulate the output dimension of the desired array, given any input dimension of your input arrays, or what we call the operands. The syntax is given as this. We have Einsum subscript string followed by the operand. The subscript strings are, placed in quotation marks and are separated by comma. Okay, while the operands are the arrays you want to operate on. So you can have like five subscript strings with a notation arrow giving you the output, the desired output array, followed by the set of operand. In other words, the arrays that you want to operate on. For example, the substitute strings representation matrix is for matrix multiplication is ij, comma jk to give us ik. Here, we want to multiply these two arrays of dimension ij and jk to be summed along the dimension j, so that the output dimension is ik. The following operations can be done with the Einsum operation. You can do dot product, outer product, transpose, the trace, or what is also known as the diagonal sums. We can do matrix multiplication. All of this can be done on matrices and vectors easily. The Einsum operation is implemented in most libraries in Python, such as NumPy. The syntax there is np.einsum. In PyTorch, you have it as torch.einsum. In TensorFlow, you have it as tf.einsum. Some other examples of subscript strings include one, you have the I comma I. Okay, I was putting I. Then we are talking of the inner product of two vectors. We have the ij comma jk, okay, annotated to ik. That we are looking at the output. We are looking at the outer product of two vectors. In other words, we are talking about matrix multiplication. The third one, we have II, okay, annotated to nothing, just II, with the annotation arrow pointing to nothing. There we're referring to the trace of a matrix. The other one, we have the IJ pointing to giving us JI. There we are doing transpose of a matrix. And then the next one we have ij. I'll put in I. There we are doing summing a matrix or an array along the axis I. And lastly, we have ij pointing to j, where we are summing a matrix or an array along the axis j. We will categorize our examples based on these listed examples shortly. First, let's look at sum of matrices. To do that, first we import numpy as np, and then I create an array A using np.a range 36. I want an array of range of 36, 0 to 35. And then I will reshape this array to 6 by 6. If we run the cell, it gives us our array. Our array is a 2D array, 6 by 6. Now we have printed the array. You can see the array. Next, let's call np.eindsum ij, okay, pointing to, okay, no output dimension, and then we'll pass in the operand. In this case, a is the operand. What are we trying to do here? We're trying to sum up all the elements of a. That's what this subscript string is referring to. So if we run this cell, what we have, it gives us 630. Now let's check this using the sum method in numpy. If you run this, a.sum gives us 630. So instead of using a.sum, we can simply use the eindsum to do the same thing, achieve the same results. It's quite fast. So we just call ij, and then the annotated arrow points to nothing. In other words, just sum it, all the elements of a. Now next, let's sum along the axis 1. In other words, let's sum along I. If we sum and put to I, we just call np.sum ij with the annotated arrow. That's a minus plus and the angle greater than the symbol pointing to I, comma a. So we have the subscript string here is ij outputting I. So in other words, we want to sum this array along the axis I. If you run this, what do we have? It gives us 15. See, it gives us a 1 by 1, 2, 3, 4, 5, 6, no, 1 by 6 array, right? If we also implement it by simply calling np.sum a, axis equals 1, what will that give us? Same results. You can likewise write this as a.sum, and you specify the axis. Running this cell results in same results. So it's either you call np.sum or you call a.sum, because a is already an array, so you can call the method sum on the array. Let's sum along the axis 0. Okay, let's sum along the axis 0. Then we call np.eindsum ij pointing to j, comma a. Passing, this is the operand, this is the subscript string. If you run this, what do we have? It gives us, okay, also a 1 by 2, 4, 6 array. To verify the result, let's call np.sum a and specify the axis. We run this, we have exactly same results. So this is summing along the column, okay? So this is summing along the what? The rows. If you sum along the columns, what we have? Sum all of this down there. If you sum along the rows, what we have? We sum this way. Now, next, let's compute the trace of A. And I mentioned earlier that trace is what now? Is the diagonal sum. So since it's a 6 by 6, a square matrix, a square array, or what you can call a square matrix, the main diagonal, elements of the main diagonal are summed up when you compute the trace. So np.eindsum, you just simply use I, comma I. You can use II or JJ or KK, but the two substrate string must be the same, okay, pointing to nothing, and then passing the operand A. If you run that, what it give us? It gives us 105. Now, to verify this, let's call the trace method in NumPy. So we'll say np.trace A. What would that give us? Return same results. If you sum the diagonal element of that A, it gives you that. So using this can be very helpful when we want to find the trace of the matrix. The next example here is I will look at matrix multiplication. So here what I will do is that I will use the NumPy package and the random.rand integer of 20. I want a random integers of 20 and the size should be 3 by 3. So I want to generate a square matrix of dimension 3 by 3 containing random integers of between 0 to 20. I would do likewise to B, same to B. So if I run this cell, what do I have? I have my A and B now in my namespace. Okay. You can print A if you want to print A. Let's see, you can decide to print. Let's print A and also print B. Let's see the result. So if you print that, this is first one is A, the next one is B. Now let's multiply A and B. You can do that by simply using np.mathmul a and b. We have seen that in our previous video when we did array manipulation, okay, array multiplication as well. So if you run this, of course, this is the result it gives to us. I'm doing this as a check to compare the result, the output with the numpy.eindsum. So for the case of the eindsum, what do we do here? We call np.eindsum and then pass in the subscript string. Now, the first array has a dimension ij. The second array has dimension jk. In other words, the column of the first array must be the same as the row of the second array. That's the rule for matrix multiplication. And what should that give us? Ik. In other words, we are saying sum, multiply these two arrays and sum them along the index j. So that is what this means. And then we'll pass in A, comma B. So instead of saying calling this math mode, we can instantly pass in the eindsum. And if we run that, what we have same results. So this is how we can use the eindsum function to do matrix multiplication. Let's proceed further where in the case we don't have a square matrix, right? So we also here we generate random integers of size 3 by 5 and B of random integers of size 5 by 3. But you notice that the column of A is same as the row of B. That's one of the rules of array multiplication. So same, likewise, we have run this, we already have it in namespace. We call np.eindsum, ij, jk, and the output array should be ik. You can see that j here is 5. Okay, so j is equal to j in of array A and B, and then we'll pass in A and B. If we run that, what does it give us? It returns, of course, a 3 by 3 matrix, which you can see if you follow our rules of array multiplication. So the eindsum does that faster for us. Okay, let's see when we are summing along the row. Now we have two arrays, A and B, and want to sum along the rows. Okay, sum along the rows. I. So here we call in numpy.eindsum, ij, jk, and it should give us what? I, to return I. In other words, we want to return the result, I, summing along what? Along the rows, and they'll pass in A, B. If we run this, what do we have? It gives us that. So he will first of all, what happens is that it does the matrix, the multiplication of A and B, and then returns the sum of the value along the row. So if you sum these values, 545, 280, 384, that gives us this 731, 3727. That gives us the next element, and if you sum this, that gives us the last element there. Now, likewise, we can sum along what now? Sum along the column. Okay, we can sum along the column. So do that, we just call the same item function, ij, jk, and it should give us k. Okay, because remember, the reason why the row here is referred to as I and the column is referred to as j is that when you do a matrix multiplication of ij, jk, okay, that matrix multiplication will be the sum along the index j to give us ik. So since the output returns ik, the row is I and the column is what? K. So that's why I'm using K here to denote the summation along the column. So if we run this, what we have return same result. So if you come to this side and also sum these values of this array multiplication along the column, will return this result that we have here. Next, let's look at the Hadamard matrix product, or what is called the Hadamard product, or element-wise product, or element-wise multiplication. I randomly generate A and B, but in this case, I have it as size 4 by 4. So do that again. We have A and B, an array of size 4 by 4. Now, to do the element-wise product or multiplication, we call np.einsum, and we have ij. Now, in this case, the rules suffice that we're not really interested in the number of column of A being equal to the number of rows of B. No, we just want it. They are of dimension ij, and should return for me ij. So if I do that, I pass in the array A and B, it returns for me a 4 by 4 array. Okay, so here what we have done here is element-wise multiplication. Next, we can uh, use this to get the diagonal matrix. So to do that, I call another array C, and I use np.array16, and I reshape it to 4 comma minus 1. The minus 1 here is I'm asking np to determine the value there. Likewise, I can, of course, I know it's 4 by 4, but I want to let them, determine this value automatically by itself. So if I run this and I print C, let's print C, and let's see what C is. To print C, it's a 4 by 4 array. Then to get the diagonal element, we can simply call np.diag of C. If we run this, what happens? It returns for us the diagonal element. And let's see, diagonal element is 0, 5, 10, 15. So it picks the diagonal element. Likewise, we can use the Einstein to do that. To do that with Einstein, we simply call np.einsum I, outputting I, and then you pass in the array C. If we run this, it returns the diagonal elements. Next is trace. To do that of trace, I will use the same array C. All I need to call np.einsum I, pointing to no output index. Okay, the output index is omitted. If you run that, it gives us the trace. The trace is the sum of the diagonal elements. Okay, and that, what would that give us? You can see it, 5 plus 0 plus 10, that's 30, which is correct. Next is transpose. In the case of transpose, we are trying to swap the rows and the columns of the matrix or of the array or of the tensor. In other words, if you have an array of I, j, we want to swap it to j, I. Of course, you can, I'm still using the array C as example. To do that, you can just call C.T, okay? Because C is an array, it does the transpose. You can use C.T or this does transpose, returns the same. But how do we do that with the einsum? We simply call np.einsum ij, returning ji and c, and we get the same. So here we can see that the transpose is simply implemented with this using np.einsum. The next here is a dot product. Here we have two arrays, okay, one dimensional array containing 5 elements, that's size 5, okay, of A and B, and we want to multiply them. This is different from the matrix multiplication. Here we are trying to do the inner product or inner dot product of two arrays, or what we can refer to as 1D array, or we also call them vectors. So we have A and B, okay, randomly generated integers. To do that in NumPy, you can just call np dots, okay, A comma B to give us 183. That's the dot product of two vectors. Okay, it returns a scalar. But to do that with the einsum, we simply call np.einsum. The subscript index or string is I for the first array, I for the next array, and then pointing to nothing. If you do that and you pass in the array A and B, what do we have? Same result, 183. Let's look at a further example. In this case, I want to consider multi-dimensional arrays. By given three arrays, A of size, number of samples, batch, height, and width. So next is B of size, number of samples, batch, and height, and C of size, batch, height, and width. Okay, the size is referring to the dimension here. First, I would specify the number of samples as 100, batch size as 20, height as 300, width as 400. And what I will do next is to randomly generate array A using the number of size, samples, batch size, height, and width. Likewise for B, number of samples, batch size, and height, and then for C, uh, batch size, height, and width. First, let's multiply A and B to have output array dimension of number of samples and batch. So you can see here that I've called by Einstein and assigned it to out, okay? But instead of using IJK, I have used unique subscript strings. Now I have used N to represent number of samples, B to represent batch, H to represent height, and W to represent width. So A is N, B, H, W, comma. What is the dimension of B? N, B, height, number of samples, batch, and height. And what do I want to have? I want to have an output. This is my interest. Okay, I want the output to be what? Number of samples and batch. So I needed to sum this array along two indices, which is what? Along the height and the width. Then I'll pass in my array A and B. If we run this already, if we run this, what do we have? It gives us our out. Let's print out the shape. Out the shape is 100 by 20. What's the number of samples? 100, batch size 20. So it tells us that giving us an output array of size 100 by 20. Now, secondly, let's multiply A and B to have the output array of height and width. Do the same thing out to np.einsom, nbhw, nbh, but same, everything is same. The only thing we have changed is the output dimension. I have it one as what? Height and width. In other words, multiply these two array and sum them along the number of sample and batch. So if we do this, what do we have? And print the shape. Was the height? 300. Was the width? 400. Now let's multiply A, B, and C to have the output array, number of samples, and batch. So A already has NBHW, B has NBH, and what is C? C is batch, height, and width, which is BHW. What do we want to get out? We want to obtain NB, comma H. Okay, so I want NBH, or rather, first I want NB. So let's do NB. There's nothing you cannot do. All you need to know is to know your desired output dimension and you point it to it. It gives you that. If we run this and print out the shape 3, what do we have? NB 100 by 20. What is N? 100, batch size 20. Likewise, if I wanted that NBH and I put NBH here and run again and print the shape, what do we have? 100 by 20 by 30. Next, which is out 4, let's call Einstein NBHW, NBH, BHW, of course, for C. But what output do I want? I want it as NHW, number of samples, height, and width. So running and print shape, what do we have? Number of samples, height, and width. If I want a trace of the output matrix 4, all I simply need to do is to do what? To call NHW and point it to no index and put in output 4. And it returns this value. So NumPy Einsom is very powerful. As a take home, it help gives us an advantage to do much more difficult array multiplication that we may not be easily achievable or that may require multiple calls to the matrix multiplication in NumPy. But with Einstein, we can manipulate the output array dimension. And that's one advantage of Einstein or the Einstein summation. Please like this video, share this video. If you have any comment, you can leave it, or any question, leave it in the comment section. I will leave a link to this notebook in the description for you to download. We've come to the end of this video. I will see you in my next video.